Thank you. And if anybody shows up to the future meetings and notice that I'm not recording, please please remind me to record it, because I apparently forgot to set it up to automatically record. Because I do want to record these, and I'll probably post them up on YouTube or something. All right, I guess that's it. So whenever I've done this with my group in the past, I've always been extremely informal about it, and there's a lot of back and forth and discussion. So please interrupt me with questions. This is not any sort of class lecture or anything like that. Ask a lot of questions. Interrupt me. If something's unclear, or if you don't believe something I'm saying, stop me and we can talk about it. But otherwise, I'm going to go ahead and stop my video and start sharing my screen. All right. Okay, so like I said, the first thing that we're going to do is just go through some very basic math things. Let me see, I'm seeing. I just got a private question, and the answer is yes. All right, so there's basically two kind of math things that I wanted to cover. One of them I'm going to go through just relatively quickly, just some like very basic properties of Fourier series and Fourier transforms. And I'm just going to go through that rather quickly, and then then I want to spend a lot of time talking about functional calculus, and that's something that we will go through a little bit more slowly and a little bit more deliberately. Okay, so let me actually get a black pen, and I am going to just write it out just because I think it's much easier to. So basics of Fourier series and transforms. All right, let me see. So, all right, so we begin with the function f of x. Sorry, I'm just trying to get back into teaching mode. It's been a couple of weeks. I just got a question from Mizuki about being able to record. I'll just send me an email after this, and after Zoom is done processing it, I'll send the file to you directly, because it is recording for me, I think. All right, so we begin with the function f of x that's defined over some finite interval, right? So we have x that's in a range from minus L over 2 to plus L over 2. And for most of the stuff that we're going to be interested in, we only care about functions that are going to be integrable, single valued and continuous, and have some finite number of minima and maxima. So it's just basically any sort of well-behaved function. And if all of those properties are true, so if it's it's a reasonably well-behaved function, then the important thing is that we can write f of x as a sum from minus infinity to infinity, a sub j e to the I 2 pi j then x over L. Right, and so the a sub j's are our Fourier coefficients. J is an index, and of course I is the imaginary unit. So we're going to see a lot of the imaginary unit over the coming days, because it shows up a lot in these equations. And of course, because of the Euler identity, we can also think of this as being something like a sine plus a cosine expansion, because we can write the exponential of an imaginary unit as a complex number as a cosine plus a sine. And of course, we can, these functions are orthogonal if for two different values of j. So that's the property that we use to find the Fourier coefficients. So we use the orthogonality. Right, and so what I mean by orthogonality is that if we integrate over our domain, L over 2 plus or minus L over 2 dx, and we have e to the minus I to pi in x over L times e to the I to pi j x over L, then we get the Kronecker delta function out of this, right? So we get just simply L times delta n comma j. And I'm assuming that folks are familiar with the Kronecker delta function. If not, again, don't hesitate to ask. But basically, it's a function that's 0 if n is not equal to j and 1 otherwise. And so we use this to get the Fourier coefficients. And so we have a sub j. You can use this property to get a sub j just by plugging it into the equation above. And what we get at the end is minus L by 2, L by 2. And we're integrating over x, f of x e to the minus I to pi j x by L. And the way that we wrote this series up here, we said that we're going from plus infinity to minus infinity. Of course, we're not actually, in practice, we don't do that. The series is always going to be truncated, and the whole utility of the Fourier series is that if f of x is well behaved, then this series will converge faster than any power law or than any finite power. The series will converge to the real representation of f of x faster than any sort of like power of series expansion. And that's the kind of useful property of these. All right, so let's see. Let me keep moving on. So this is the expression for the inverse transform when we have a Fourier series. And I'm going to often write this as, so this is how we get our Fourier coefficients. And I would often write this as f of k, right? The Fourier transform of this thing is, and I'm going to be very loose with my notation on a lot of these things, right? F of x e to the minus I kx, where k is our wave vector. And this is going to be 2 pi j over L. I feel like I'm messing something up here. Hold on. And I'm off to a rocking start. I think we're good. This should be a plus though. No, we're good. Sorry. All right, and then the other thing, I guess the other point is we'll be interested in the continuum limit. This is something that we will take sometimes, which is basically when we let L go to infinity. Right, so we let the size of our domain go to infinity, and in this case, we can write f of x, instead of it being a series, we replace the series with a sum, or I'm sorry, an integral over the variable j. Variable aj, a sub j, then e to the I to pi j x by L. And we use the same definition of k, and we do a change of variables so that we end up with this going as 1 over 2 pi integral dk. Then e to the, sorry, and then this would be now what we called f hat above, f hat of k e to the I kx. All right, fair enough. Then the thing that we really care about, and what we're really going to exploit with Fourier series extensively, is going to be the just some special properties that they have. And so the main thing that I wanted to get to with this reminder about Fourier series are the useful properties. And what, I'm missing a negative sign. No, this is the back transform, so it should be plus ikx. All right. So let me see. All right, so some of the useful properties of the Fourier transform, and things that I'm going to use extensively as we go through a lot of the the notes, right? So useful properties of Fourier transform. And a lot of these are really basic, but it's something that I just find that people often forget, and so I just want to remind them. The first one is that the k equals 0 mode, right? So the result of the Fourier transform of the function is the integral of the function. Right, and you can see that very easily just by writing out the equation, right? So if we look at where k equals 0, so minus infinity to infinity dx, then we have f of x, and then we're doing the inverse transform, or we're doing the forward transform, so this is times e to the I minus I k equals 0 times x, so it's just e to the minus 0. And so then, of course, this is just the integral of the function, right? It's just integral dx f of x. And so this is a useful thing to always have in your mind, because if we do an example where we say are calculating the Fourier transform of a field of charges, for example, one thing that you will always want to ensure if the system is charge neutral, that the integral over the whole domain should be 0, right? So that means that the 0 mode of the function in Fourier space should be 0. Another very useful property is the one for derivatives. Right, so we can evaluate derivatives in Fourier space. So if we just look at df dx, right, so we're looking at the derivative of the function in real space, right? This is going to be d by dx, 1 by 2 pi, integral dk, f tilde of k, e to the I kx. Right, and on this right-hand side, so all we've done here is replace f with its inverse Fourier transform, and then we take d by dx, and the only place x shows up is in the exponential. And so this is 1 over 2 pi dk I k f tilde of k e to the I kx. Right, so we can get the derivative of a function by Fourier transforming it, multiplying by I k, and then inverse Fourier transforming it, and that would give us the derivative of the function in real space. So in other words, and I'm going to start abbreviating the Fourier transform operation in this manner, right? So we can say that the Fourier transform of f prime, or df dx, this is going to be equal to I k f tilde of k. And similarly, if we do that operation again, we would just be taking two derivatives. So if we have the Fourier transform of f double prime, or d squared f by dx squared, then we just pick up another factor of ik, and this just becomes minus ik squared f tilde of k. Right? And so for things like diffusion equations and the Poisson equation, this is a really convenient way to represent them. All right, a couple more things I want to make sure that we point out. So convolutions, this is going to show up a lot. Convolutions. Right, so a convolution operation is going to be defined. So if we say that f of x is a convolution of two functions, that would be minus infinity to infinity dx prime, g of x minus x prime, h of x prime. And I'll often abbreviate this operation as just using this notation that we've just kind of adopted in our papers. I'll put it in parentheses with an asterisk to indicate a convolution. And then the resulting variable is, the resulting function is going to depend on x. And so you see that we have x prime in both of the equations, but we're integrating out x prime. So the resulting function is only going to depend on x. And the thing that's nice is that you can show that the Fourier transform of f of x is just the product of the Fourier transform of g and h. Right? So this is the convolution theorem. And so f tilde of k, this is can be written as g tilde of k times h tilde of k. Right? So that's a useful one that we will use a lot. Another one that we will use in the last one or two lectures of this series that I'm planning, integral of a product of functions. So if we have something that's like integral dx of just h of x times g of x with no convolution operation, you can show that this can be written as a Fourier series where we have sum over k, q tilde of k, h tilde of minus k. Right, so this is a replacement that we will occasionally use down the line when we start evaluating some of these more complicated Gaussian integrals that we'll eventually get to. And speaking of Gaussians, the Fourier transform of a Gaussian is also a useful thing. It's a Gaussian Fourier transform. All right, so if f of x is 1 over 2 pi a squared, so I'm going to write it as a normalized 1D Gaussian, e to the minus x squared over 2a. Then f tilde of k. Right, so if you plug in this f of x and go through the and analytically evaluate the integral above to get the Fourier transform, it's a little bit of algebra to do it, but it's not that bad, and you end up with e to the minus k squared a squared over 2. Right, so the important point here is that the Fourier transform of a Gaussian function, so this is a unit Gaussian, is in Fourier space also a Gaussian, just with a different standard deviation, right? So sorry, that should be a squared down here. So when we go to Fourier space, the a squared goes from the denominator up to the numerator. But otherwise, it's still a Gaussian. And we know that we started off with something normalized because if we look at the k equals 0 mode here, then if we evaluate this thing at k equals 0, we get e to the 0 or 1. And so that's consistent with this being an initially normalized function. Let me see what else I want to make sure to say. Yeah, of course, all this stuff also works in higher dimensions. I don't think there's a whole lot really to say there. You can just simply say real quickly in higher dimension, right? Because we will often be doing this in 3D. Then I use an underline to indicate a vector in my usual notation. So I guess keep that in mind. Then we'll have integral dr f of r e to the minus I k dot r. And then if we have a Fourier series, f of r is going to be, so if we're dealing with finite size systems, it would be 1 over v sum over k f tilde of k. Right, so the Fourier coefficients e to the I k dot r. Or if we're in the continuum limit or the thermodynamic limit, where we're dealing with the integral transform, we would say f of r is going to be 1 over 2 pi cubed in 3D, then dk f tilde of k e to the I k dot r. All right. Okay, so those are some basics. The other thing that I wanted to say before we get into the actual calculus of variation stuff is to just remind everybody about the Dirac delta function, because this is also something that we are going to use a ton as we go through some of the StatMech stuff starting next time. So Dirac delta. There are a bunch of ways of introducing and defining this thing. It's usually, at least the way that I see it defined, is as a function that performs an operation where basically if you multiply a function by the Dirac delta function and you give it an argument x minus a times f of x, it returns that function evaluated where the argument of the delta function is 0. Right, so this is our f of x, and it has a whole bunch of kind of unique and interesting properties. One of them is that it's a unit thing, so it's normalized, right? So delta of x is equal to 1. It will often be described as an infinitely short pulse, so like a Gaussian distribution in the limit where the the standard deviation goes to 0. That's another way that you can think about this function, right? So if you imagine a Gaussian distribution and then you shrink the standard deviation, so I think I was using a above, so as a gets smaller and smaller, then a delta function basically just becomes an infinitely sharp pulse at x equals 0. And it's going to be 0 anytime the argument is for it is non-zero. Right, so delta of x right, that's kind of the key property. And what else do I want to say about the Dirac? It has units. That's something else that we should always keep in mind. So delta of x carries units. And the units are going to be 1 over the units of x, right? And that comes back to the normalization that we have above, right? So if it's going to be normalized, it has to be integrate to 1 so that we get a dimensionless number at the end. And so that means that delta of x has to have units of 1 over x to cancel out the units on dx, right? So delta of x has units of 1 over whatever the units of x are. Let me see. So as an example of where we will use, let me say one more property of this thing. So you don't necessarily have to pass just a simple scalar into the delta function. You can also pass an entire function into the delta function. So for example, if h of x is a function that has, I don't know, we'll say n sub h zeros, then you can do an operation like integral dx delta of h of x. And so we're integrating over the whole domain. And because the integral of the delta function is going to always give you a unit pulse every time the argument is equal to 0, then this thing would just simply be return n sub h. Right? And so you can kind of use this delta function to enforce constraints, because basically you can force anything else that's under this integral sign to be just ignored or turned off or set to 0 anytime that the argument of the delta function is not equal to 0. And as an example of that, you can consider the density of states that's used to define the entropy, right? If you write that for a classical system, you can write it using a Dirac delta function, right? So the classical density of states right? So if you have omega of E, right? So the number of states that have a particular energy E, you can write this as 1 over h to the 3n factorial, integral dp to the n, integral dr to the n. And then you just want to know how many states you have that have some particular value of the energy. And so the way that you set this up is you take the energy that you want. So that's the one that's on the left-hand side. And then you have the kinetic energy of the system and the potential energy of the system that you subtract off. Right. And so every time that the kinetic plus the potential sums up to E, the argument of the delta function will be 0. And so then every time that this whole thing, that the argument of this thing evaluates to 0, you'll accumulate another increment into the density of states. And so this is a way that you can count the states. Let me see what else. All right. And so delta functions are something that we are going to use extensively to enforce constraints as we go through this. All right. Any questions about this kind of quick overview stuff? I realize it's super dry and just kind of a list of facts, but it will get more interesting next time, I think. Okay, so now let's switch gears and talk about functionals. So there are a bunch of good resources for this. For learning about functional calculus, I don't have my list of resources on here. Everything that I first learned about it, I took from the appendix that's in the the textbook by Glenn Fredrickson, The Equilibrium Theory of Inhomogeneous Polymers. Sanat Kumar is here? Wow. Yeah, I should do Fourier transform of a delta function. That's a good point. Yeah, let me. Because we are going to use the hell out of that. So that is delta of, let me make it x minus a. This is 1 over 2 pi, minus infinity to infinity, dk e to the I k x minus a. Right, so in other words, the delta function in real space, in Fourier space, it's basically just a constant. And so this is something that we are going to use extensively when we go forward. Like we're basically going to use a combination of the delta function with a function as an argument and enforcing it as a constant, and then writing that all of that in sort of the functional version of Fourier space to enforce constraints like incompressibility in our partition function. So thanks enough for calling that out. All right, so now let's go on to functional calculus. Okay. So again, I'm going to be a little bit loose with how I'm going to derive all this stuff. I'm going to follow the approach that's done in Glenn's book. It's a little bit different from the way that a lot of other people develop functional calculus, but it's, well, it's how I learned it. So it's how I teach it. The whole idea with, functional calculus and the contrast of it with sort of the standard, function calculus, is that rather than having a quantity that depends on the value of an input at some particular location, it's going to depend on the value of an input over an entire domain, right? So the way that I'm going to define a functional, it's going to be a mapping between a function that's defined over some interval and a number, right? So it's going to be a mapping between a function f of x right? So it'll be defined on some interval, a to b, and a number f, right? And so I'm going to denote this, so something that has a functional dependence. I've already kind of used this a little bit above with square brackets, right? So this indicates that f has a functional dependence on the function f. And so it's going to depend on the value of f over the entire interval. And so the simplest function that you could ever functional that you could ever possibly imagine, and again, I'm following Glenn's notation by the way that I'm writing this stuff, is a to b dx just f of x. Right, so the result of this integral depends on the value of f over the entire domain, right? And so this is, we would refer to this as a linear and local functional, right? It's linear because it's first order in f, and it's local because it only depends on x at one position at a time, right? Then we could have, say, a nonlinear but still local functional, right? So another, I'm just incrementing a subscript here to denote that these are different functionals, right? We could imagine writing something like this, f of x squared. And again, we would call this one a nonlinear, but still local functional, right? So it still only depends on one x position at a time, but it's nonlinear because it's squared. I guess some of the more famous ones that show up, there's a very common functional that shows up in like Landau-Ginzburg theories of phase transitions. So we call that one F3. So it doesn't only have to, functionals don't have to depend on just the function itself. It can also depend on derivatives of the function. So we have a to b dx. And so this is one that shows up quite a lot in theories of phase transitions, squared f of x to the fourth. And I'm ignoring all the coefficients just because then df dx squared, right? And so, this is still a functional of f, right? And this is something that shows up a lot as something to be minimized uh, with respect to, say, if f of x were, say, for example, a density field, you could minimize the free energy of the system with respect to variations in that density field. And that's kind of the machinery that we're going to build up. Let me see what else. I guess let me list these other couple of examples that we have. This is very closely related to something that's like the form that we're going to have as we get back to our stat mech later on. Dx prime a to b. So if we have f of x, k of x, comma x prime, and f of x prime, this is just, again, it's another example of a functional form, and this is one that we're going to see a lot, where f of x is going to be something like a density, right? So it'll be a density at two different positions, and then k of x and x prime will be something like an interaction potential, right? So it'll tell us about the potential energy between the stuff at x and x prime. All right, so I hope we're all clear at this point on the definition of functionals and what they are. The thing that we're really going to care about is actually doing calculus with them. So, and to do calculus with them, we're going to need two things. We need to be able to take derivatives, and we need to be able to do integration. And so the way that we should imagine taking a functional derivative, and we'll talk more and try to build some intuition on exactly what this works, but the way that the functional derivative rules are derived, at least in Glenn's book, is that if we have our function f of x, we're going to take it, and at every position along the domain, we're going to perturb it just a little bit, right? So we're going to perturb, so we'll call this functional derivatives. So I'm going to say delta f of x, right? And so we're just going to slightly kick our function around over the entire domain, right? And the way that we derive the derivative rules is by writing out. What we're going to be able to do is show that we can write this as f plus delta of f. Let's see, this is going to be f of f, and we will be able to go through some expansions and rearrange this so that we have something like, sorry, times delta f of x. Then there will be plus a 1 over 2 factorial integral dx, integral dx prime. I'm dropping the limits on the integrals just because I'm getting sick of writing them, but it's still, you should imagine that the limits of the integration are still there. Times delta f of x times delta f of x prime. All right, and so each of these gamma sub I terms are going to represent the Taylor expansion of this function. And so these are basically where the like df dx would show up if we were doing a regular Taylor series expansion, right? And so it has a very similar form where we have the function evaluated at the original point f, then we have the first expansion coefficient, right? It's responsible for the first variation, and then it's multiplied by f minus what we're perturbing around, which is f plus delta f, and so we have just the delta f. Then we get the second expansion coefficient, and again, we will work through examples to see where all this nonsense comes from. And the way that we're going to write functional derivatives is that we will say delta f of x, or variation of f with respect to f of x, right? This is going to be just simply defined as gamma 1 of x. The way that we write second variational derivatives, this will be delta f of x, delta f of x prime. This is going to be gamma 2 of x, x prime. and so on. All right, so let's work through an example. I mean, for the most part, these derivative rules, once we've worked with them enough, they kind of, you build some intuition and they have a very close analogy with regular derivative rules. But it's nice to have the kind of systematic way of developing them. All right, so let's go back to our F2 and let's look at F2 of F plus delta F. All right, so remember, if we scroll back up, F2 was the quadratic function, so that's the one that we're going to use. All right, so this is now integral from a to b dx. So we plug in our f of x plus delta of f plus delta of f of x. All right, so all we've done is just write down what F2 is. And now we're going to start expanding this thing, and then we're going to play a game of manipulating it into the form that we had above. All right. And we have to play some tricks when we do this, and a lot of them are not going to be obvious, but it's one of these things that you kind of develop with practice. So the first thing that we're going to want to do is to rewrite this so that we have both an integral over x and an integral over x prime. And so the way that I go about this is say integral dx, integral dx prime, and I'm again dropping the limits of the integration just because I'm lazy. And we'll say f of x plus delta f of x times the Dirac delta function of f of x minus x prime, and then it'll be multiplied by this other term, right? So this is how we plus delta f of x prime, right? And so this lets us practice with the Dirac delta function a little bit as well. And since this term doesn't depend on x prime, we could take the integral over x prime, and kind of the defining property of the delta function is that it would just return anything that it's multiplied by, evaluated where this thing is going to be 0. And so that's where x prime is equal to x. So we would just get this thing back if we did that. All right, so the next game that we're going to play is to now multiply this whole thing out. So we have the delta function, that's x minus x prime. We have our double integral, and then we're just going to multiply this whole thing out so that we end up with a number of terms. So this is going to become equal to integral dx prime. Then we'll have delta x minus x prime, right? So that's going to multiply everything. And then I'm going to write it as, so we have f of x prime plus f of x delta f of x prime, right? So that's the first one times the second one over here. Then we have plus f of x prime delta f of x prime. And then we have the term that's just the two deltas, right? So then we have plus delta f of x times delta f of x prime. And we close our braces. And so now we can start manipulating this back into the form of this thing that's like that we're going to take as our defining form for the derivatives. So the first one where we have f of x and f of x prime, right? So this is going to be integral dx, integral dx prime. We have our delta function that's going to help us out a bit. So we have, f of x prime times delta of x minus x prime, right? So that's from the first term. And of course, when we integrate this, we integrate over x prime, we'll go back to the original starting function. But we're not going to quite go there yet. The next two terms that we have two terms that have an f of x times a delta f of x. And I have a mistake in one of them because this one should not be x prime. Sorry about that. Make sure that if you're writing this down, make sure that you fix that. This should not have a prime on it. All right, so we have two terms that are basically the same within the change of variables, so we can write that as plus 2 dx prime. Still have our delta function, x minus x prime. f of x times the variation of f at x prime. And then we have the last term that's just going to be the delta function. So then we have plus integral dx, integral dx prime, delta of x minus x prime, variation of f of x times variation of f of x prime. Okay, so we're almost done. So this first line, let me write this first line here, if I can get another color, this one is just going to be, if we take the integral, again, we can integrate over x prime. The delta function is just going to give us f of x back at f, and so that we end up with integral dx f of x squared, right? And so then this is our f of f that we had before, right? And so again, we're trying to manipulate everything into this form. And so now we have our first term. And now we need a term that's integral over dx times just one delta of f, and that's going to give us our first derivative, our first variational derivative. And so we have something with just one df, but it has two integrals on it. So we're going to just take the integral over x prime. And so this one, I'll use red for you, just becomes 2 times integral dx f of x delta of, or delta f of x prime. And then the last one is basically already in the form that we need, right? So if we go back up, we need a 1 over 2 factorial. And so we have to multiply and divide by 2, right? So we're going to, in here, we're going to multiply and divide by 2, and we'll have the form that we need, right? So what this tells us then is that the first variation of this f2 with f of x is just simply 2 f of x, right? Because that's where the gamma 1 would be in this form that's above. Yeah, in red, that's, yeah, it's delta, it's the variation of the function f of x. Oh, I see what you're saying. The prime again. Yes, I missed the prime. Thank you. Yeah, there was another mess up with the prime here. All right, so the first variation of f2 with respect to f of x is just 2 f of x. And again, if we think back, like if this were just y equals x squared, you take the derivative d by dx, you get 2 times x. It's kind of similar to that, that type of an operation, and you can think of it in that way, at least in a very loose sense. The only other sort of wrinkle here is that we started with a functional, and so taking this variational derivative killed off an integral, right? So we killed off an integral sign with that. And then the second variational derivative, or the second functional derivative, is just where gamma 2 would be in the equation above, right? So that's going to be 2 times the delta function, right? So d squared f2 df of x df of x prime, right? So the only thing that survives here, this is just going to be 2 times delta function of x minus x prime, right? And so that's how we get there. And you can derive these kinds of rules for all of the different functions that are defined above. We're not going to go through all of them, but this is the kind of thing that is going to show up a lot as we go through some of the a lot of our a lot of the StatMax stuff that we will start to get to next time. And intuitively, the way to think about it, so if we have, let's see, if we have our f of x, I'm just going to sketch a domain, right? So this will be a, this will be b on our x-axis, and maybe we have some function f of x. The way that we defined our functional f2 of f, right? We said this is integral a to b dx f of x. And the sort of intuitive way to think about what we mean by a functional derivative is when we say df2 df of x. So the 2 in gamma 2. Let me So it comes from the fact that this the series definition that we started with has this 1/2 factorial in it, right? Like the coefficients of a Taylor series. And so we have to multiply and divide by 2. And so the divide by 2 is the thing that stays out in front when we define gamma. Yeah, okay. And so again, the sort of intuitive way of thinking about what this variational derivative means is that, you know, we're basically picking a value of x. So I'm going to make this delta function of f of x prime. We're going to some location x prime and then just poking the function a little bit, right? We're just perturbing the function a little bit and then asking, how does this integral change, right? So how does this integrated thing, whatever this functional argument is, how does that change when we go to some specific location x prime and change the value of f a little bit, right? And so we're going to, again, the thing that we're going to build up to working with is that we will have free energy functionals of either densities or chemical potential fields, and we'll want to minimize those with respect to variations. All right, so, and that actually brings me to the, let me see. Oh, there is one definition that I want to point out, or a couple of functional derivatives that I want to point out just because they're, again, going to show up a huge number of times. So we defined f4 above, right? So that was the thing where we had integral dx prime, f of x, k of x, x prime, f of x prime. It's worth asking, you know, what is df4 df of x? And so it's df4 by df of x. This comes out to be just, you can show that this is 2 times dx prime, k of x, x prime, f of x prime. Right, so that's one thing that you can prove. Another one that we will use extensively is are the derivative rules when we are the variational rules when we are looking at derivatives of f of x. Right, so you can also, so this is going to be another important one for us. For a system with periodic boundary conditions, right, so if we're dealing with a system that has periodic boundary conditions, what that's going to mean is that at the ends of our domain, the function is going to be equal to itself, right? So f of a will be equal to f of c. I don't think that I wrote this guy down above, but if we have something that's like a to b dx, and it depends on the derivative of f, right? So df dx all squared. What you can show is that df7 df of x, this is minus twice the second derivative of f, d squared f dx squared. And this is something that will show up when we, again, when we run into like Poisson's equation and stuff like that. It's going to be convenient to have this one also in the back of our mind. Let me see. The last couple of things, so there's a functional chain rule. Right, so if we have if f depends on g, and g depends on the function f of x, df of x, then the way that we write down the chain rule is that this becomes dx prime variation of f, g with respect to g, variation of g of x prime times delta g of x prime and delta f of x. All right, what else do we need? And I guess basically the unit function. So if we do the variation of f of x at f of x prime, this is another one. This just returns a delta function. Right, because again, this is sort of asking like, what does the value of f at location x do if we change the value of f at location x prime. And x is not going to do anything unless we're doing that at x prime. All right, so I guess one more thing that I want to say about derivatives. So, right, so extrema problems. So if we're trying to do a min or max problem, the way that we write that is that we say that the first variation of f of a functional, right, so this is, I'm sorry, I'm just going to state this more simply. So the functional f of f has an extremum when, basically when delta f of f equals f star equals 0. Right, and then f star is going to be the value of the function, or the distribution of the function that that leads to the extremum. Right, so this is going to be the function evaluated at the extremum. All right, so I realize we're coming up on an hour. I'm going to try to finish relatively quickly, but there are a couple of things that I need to make sure that we define. All right, the next thing, okay, so the next thing is functional integration and what we mean by functional integration, because this is where we're ultimately going to be going. And so basically for functional integration, so if we want to integrate over a function, what this basically means is that we're going to we want to integrate over all of the possible shapes of a function, say f of x. Right, so if we're going to integrate a functional, integrating f of f, right, this means evaluating the functional big F for all possible shapes of f of x. Right, means evaluating f for all possible shapes And so again, where we're going to be headed with this is that our partition functions are going to involve functional integrals over chemical potential fields. And that's where we want to get. And so this would generally mean what we're doing, and the way that I will denote a functional integral is I'll use a script df. And so this indicates that we're doing a functional integral over f of x, and then we're integrating this guy. Right. And again, the way that I sort of intuitively think about this is that, if I sketch my generic function again, I find these functional integrals, and typically the way that we're going to evaluate them is going to be to somehow discretize them over the domain. So we would say evaluate the function on a grid. And when we go to evaluate this functional integral, so if we discretize this thing, and then our functional integral is going to become I, right? So this n is number of discretization points. This would be like going to minus infinity to plus infinity df1. So this would be, say, the point at f1, the point at f2, point at f3, and so on. And so basically we're going to this first point, and this first integral represents, taking this thing and going from minus infinity to plus infinity, and then asking how does the overall integral change. Then this represents doing it at the next point, to, and then all the way up to df minus infinity. infinity um, n, and then the function evaluated, and then we evaluate the function at these discrete points, right? And so this notation up here is just basically the continuum version of this thing down here, right? Um, let me see. So, all right. So this then lets us define a couple of other things. So there's basically three other quantities that I want to define, and then we can, I'll stop talking and we can call it a day. The next thing that I want to define a little bit more carefully is the Dirac delta functional, right? It's something that we mentioned a little bit up thread a little bit. So the delta functional. So if we have delta of f minus g, right? And those are both functions of x. This thing is going to be 0 unless f of x is equal to g of x at every position along the domain, right? This is, right, unless f of x is equal to g of x for all x in our domain, a to b. And it still has a very similar defining property as the original Dirac delta function. It's just that instead of having a simple integral, it's going to be a functional integral. And so we'll have f minus g, and if this is times a delta functional f of f. Wait, sorry, I want to integrate over f. This returns the functional evaluated at g. Right, and so this is a way that we can do things like prescribe density fields. Let me see. Another very important one that we're going to use. So if we discretize a density functional, right? So a discretized Dirac delta functional. Right, so if we have delta of f minus g, right? So if we discretize our function into a series of grid points, this becomes the product of the delta function at each grid point, right? So it'd be delta of f of x I minus g of xi, right? So we multiply a single like normal Dirac delta function at each grid point, and we just make sure that the functions are equal at the two grid points. And if we go back to, if we recall from above, we can write these delta functions in Fourier space, right? So we can write this as, right, so we can write each term, and by each term, I mean each delta function. So each term in this product of things being multiplied together. Right, so we have delta of f minus g. This becomes 1 over 2 pi to the m, product over I. And then I'm going to use the notation, let me see. Minus infinity to infinity. All right, so we have to do an inverse Fourier transform for each one of these, for each delta function. So at each position, we're going to write this as an inverse Fourier transform. And so this becomes dw of xi. And so instead of this w of xi is going to play the role of our wave vector k, and this is e to the I w of x times f of xi minus g of xi. Right, and so again, the thing that we should be recalling here is, scroll back up and find it. is this property of the delta function. The only thing that's different is that we have, instead of k, I'm writing it as w of xi, because we need to keep track of something that's separate for each one of these delta functions that we're integrating over, right? And so it's, you can just think of them as being just different wave vectors all multiplied together. And so, so if this is the discrete version of this delta function, we can go back to the continuum limit, and what we see is that we have this this product of exponentials all taken together, and since we have exponentials that are going to be all multiplied together, then all of those multiplications turn into a sum, and so when we return to the continuum limit, we end up with an integral in the argument of the exponential. Right, so upon restoring the continuum limit, I realize I'm going a little bit quick because I didn't want to keep us here too late. Right, what happens is that this delta f minus g, right? So we have integrals over the value of the function w of x at every possible position. So that goes back into a functional integral over the field w. And then because the exponentials are all multiplied together, we have a sum of terms. It's going to be I, w of xi, then the f of xi minus g of xi. And we have those terms added together over and over again. And so again, in the continuum limit, that becomes also an integration. And so then the overall thing becomes e to the I integral dx w of x. Then this is multiplied by f of x minus g of x. Right, and again, this is a form of a functional that we are going to use quite a bit in the coming couple of days. Okay, then let me see. I have two more things that I wanted to get through. One of them is going to be, so let me say definition. Oh, somebody just private messaged me to not use I as an index, and that is a very, very good point. That was a terrible decision. So I'm going to make this J. Everything that should be a J, I'm going to come up here and label it in red so that it's hopefully more clear. Yeah, so this I here is the imaginary unit. The subscript that I had foolishly written as J should, or as I, should be all be J. Yeah. So I also have a question that says, we end up with an integral over the contributions of the delta functions at each point in space we're evaluating, where the weights are given by W. Yeah, if this is the integral that you're referring to, then yes. Yes. Right. Next couple of things that we're going to need. So one of them is the definition of a functional inverse, dx prime. X prime, x double prime. So in real space, the definition of a functional inverse is kind of cryptic looking because it's, if we take the function and multiply it by itself and integrate over the cross argument, we end up with this weird delta function result. But the way that the easiest way to understand the definition of a functional inverse is in Fourier space. Right, so if we have a tilde of k times a tilde of inverse of k, so this should be right? This is just going to be 1. And so this is going to be a really useful thing for us, again, and for reasons that we will see later. And so this thing is the existence of a functional, of the inverse of a function, is not always an easy thing to prove, but generally speaking, if it has a well-behaved Fourier transform, then it's going to be something that we can invert. We might not always be able to do it easily analytically, but it should be well-behaved if it has the existence of a Fourier transform. And so then again, like the -1 here just represents the functional inverse of the function a. All right, and the last thing that I want to define, or that I want to write down, are going to be the things that we are going to use to death as we go through the field theory stuff next time. And these are going to be the Gaussian functional integrals. All right, so if we have something that looks like, and I'm going to have to write quite large to make this clear, so dx prime. And again, I'm borrowing the notation from Glenn's text, x prime, and j of x prime. All right, so if we have an exponential, so again, this hopefully looks a little bit like the Gaussian that we wrote down before. Right, so if you remember, we had something that was e to the minus x squared over 2a squared. So instead of having it over 2a, we have the a in the numerator, but it's basically the same thing that we had from earlier in the class. We can write this as like in the sort of functional version of Fourier space. And I have to write, this equation is a hot mess. There's a normalization factor, but I'm going to leave that off for a moment. So this will be -1/2 integral dx prime f of x times a of x prime. And then it's a inverse, right? So the functional inverse of a is what shows up. Then times f of x prime. And then still inside the exponential, we have plus I integral dx j of x times f of x. Right, so this is all inside the exponential. And then this whole hot mess is divided by, I'm going to cheat and copy this part. Yeah, and this just simply plays the role of a normalization factor. Right, and again, the analogy that we should have in mind here is that this is equal to, I guess I should make this 1 over 2 pi a squared to the 1/2. Right, we can write this as integral dk e to the k squared minus k squared a squared over 2 then times e to the I kx, right? So that's the inverse Fourier transform of the standard linear Gaussian as a standard function. And then this is going to be something like a quote unquote Fourier transform of a Gaussian functional. Right? And so this is going to be something that we use pretty extensively next time when we start going through what we call the particle to field transformation, or the Hubbard-Satanovich transformation. And I also want to give the version of this expression when we have the other sign. So again, I'm going to cheat and just copy all of this. So copy, paste. And so there's just a couple of small changes that I have to make to give the other version of this. So if this is plus 1/2, then the only thing that changes is that on the right-hand side, is that the imaginary unit goes away, right? So I deleted the imaginary unit that was here, and on the left-hand side, we have a plus 1/2, right? And I also want to clarify that these two Gaussian functional integrals, I mean, again, I want to emphasize that these are things that we're going to use pretty extensively. We're not going to care too much about the denominator. The denominator here is basically playing the role of the 1 over 2 pi a squared. And it's difficult to evaluate it unless you've actually discretized your system. And I'm happy to point people to references for showing how to evaluate it. But this is going to be kind of the key for some of the particle to field transformation stuff that we're going to do. And I also want to clarify that these equations only work if a of x and x prime has a functional inverse. Right? So there will be cases where that just simply doesn't work. And usually what that means is that it's going to be continuous and differentiable and positive definite. And that'll let us get through it, do this functional integration. And hopefully you can sort of see what this is going to look like. I mean, this looks suggestively like a Boltzmann factor where we could imagine that this is e to the minus 1/2 density potential energy function, then density at another position. And so we can use that to decouple the interactions between the particles. All right. Sorry that went a little bit long. And I promise we'll actually we will do only StatMech next time, and it'll hopefully be more interesting and less dry than all this math stuff. But we will use a lot of these properties pretty extensively over the next couple of weeks. Are there any last minute questions? All right, I guess if there aren't any more questions, I will stop this. I will post the PDF of my notes on I guess on my group's website, which is rrgroup.cs.upenn.edu. And let me see, how do I stop sharing? So the PDF of the notes will be up there, and we'll post a link to wherever the recorded versions end up as well, if anybody is interested in them. All right, same time tomorrow. I will see you all then. Take care. Bye. Actually, so Carol, if you're still here, did I answer your question?
Oh, yes. Well, no, I guess I was just trying to make the point. Yeah, I don't know if you saw my other private message, just how it connects, how it has a physical basis for interpreting how we evaluate the density fields in SCFT simulations, for instance. Right. So the fact that we get an integral over the contributions of the delta functions at each point that we're evaluating in space, weights are given by W, is connected to the fact that for that when we get outputs from SCFT like density field values, those have a physical basis in how we're evaluating the delta functions present in the molecular potentials that we use to construct the Hamiltonians.
Right.
When we write the Hamiltonians, they're based on potentials that have some delta functions.
Yes.
To describe the densities, right? And so that translates all the way into the densities that we get, the density field values that we get, because of this mathematical property that you were pointing out.
Right. Yeah, I mean, so I guess the way that I interpret the W fields is a little bit different depending on how you derive the field theory. So I guess, do you typically derive it using the delta functionals, or do you do the Hubbard-Stojanovic transformation with the Gaussian integrals?
So yeah, okay. So yeah, if you do it. If you do it with a Hubbard-Stojanovic transformation, I think it's a slightly different interpretation, right? But I think it all kind of comes back, in a sense, what do I mean?
I mean, yeah, it does all sort of come back to kind of having a similar meaning, but
Yeah,
it's
because with the Hubbard-Skrutanovich transformation, you're taking advantage of the definitions of the delta functional with the Gaussian integrals, right?
yeah. You don't necessarily have to use the delta functionals at all with Hubbard-Skrutanovich.
That's true. Yeah. Yeah.
And the way that I'm going to present it, we're not going to.
Okay. Okay.
Yeah, and well, what you're saying actually gets to a really weird and subtle point that I've never really completely understood. Because if you, the thing that's kind of funny is that if you go through the particle to field transformation, like strictly following the way that he does it in the book, where if you you introduce delta functionals for the densities and then integrate out the density fields, you end up with a different partition function in the end than if you just do the if you just throw the Gaussian integrals at the thing from the start. Because the normalization factor, like those denominators, end up in the numerator when you do it the other way, right? Because you're, let me see.
But is that just an effect of like forward and backward Fourier transforms? Like how you define the forward and backward Fourier transform, right? Because like if you define the backward Fourier transforms in opposite ways, that volume factor just ends up in the numerator or the denominator. Do you know what I'm talking about?
Yeah. That's a good point. Yeah, maybe so.
I haven't worked it out myself though, so that's just a shoot from the hip kind of response.
No, it's an interesting point. Like, but the well, it's not obvious to me how that would work. And you certainly don't want it to just go away, because this thing,
right, you need it there.
Like, well, yeah, and it removes some of the UV divergences that can show up in the theories. If you trace this thing all the way through and then do like the Gaussian fluctuation.
Okay.
Analysis. Yeah, I don't know. I think we will certainly get to continue this conversation more as we actually get into the field theory.
Yeah. No, thank you very much for the great lecture. It's been a long time since I thought about this kind of stuff, so it's good practice for me.
Good.
Yeah, really appreciate it.
Yeah, no problem. I'm delighted so many people showed up.
Oh yeah, no, this is great, and I think it's always nice to have these kinds of lectures and then some of the conversations that ensue from it, because I think every time you revisit one of these topics, you get a little bit more out of it from a physical insights perspective, right?
Yeah, definitely.
Yeah, but yeah, anyway, I should probably drop off. Got to get back to work, but
yeah, same here.
And have a great rest of your day.
Yeah, you too. Take care.
All right, bye.
Bye.